All right, so we are in the middle of discussing how to compute limits on two or more variables. Okay, let me just be sure. We'll postpone this one later. Um, okay. All right. Um, so this is the criteria that I wrote down earlier for function of two variables. Okay, so limit exists if uh, it's independent of direction of approach. So in fact, it is simpler. In this case, it is simpler to disprove limit exists. Okay. To show limit doesn't exist. How to show limit doesn't exist? Find two approach in which the results are different. Okay, so for example, this one here. Um, let's pick up some problems. So for example, this one here, xy over x squared plus y squared. Mm, So we're looking for directions, which gives you a different result here. So through lines y equal kx. So this is k. So you approach this one. Okay. So then this gives you this one. And limit x y equal kx. Y kx x squared kx squared. Okay, so this is the limit of just one variable, okay? And this becomes kx squared. And here you get x squared, but 1 plus k squared, okay? And of course, the x squared cancels and give you with this one. So then just plug in two values when k equals 2, right? The limit is let's see, 0, that's 0. K equals 1. The so-called limit is 1 half. Okay, so then this shows you that limit does not exist. Okay, All right. Just a remark. Um, when we plug in, we substitute this, and end up with same value. We still uh, cannot conclude the limit exists. Cannot conclude limit exists because the approach can be anything. So this tells you that any approach like this is the same, this approach. But in fact, there are many more approaches. For example, this one. So many more approaches. Okay. So why is not enough? There are many more approaches. Okay. So in this case, it is really easier to show limit doesn't exist than to show limit exists. Okay. So far, the limit exists is just you can plug in numbers and it gives you numbers, or you can do factorizations. Okay. Questions?
No questions.
So far? Okay. All right. So then let's just do this, what we call the polar substitutions. Okay. This polar substitutions means that if you have a point here, and you think this is theta and this is the r, okay? So in this case would be x is equal to r, the cosine component, and r is the sine component. Okay, so r is, say, non-negative, and theta is between 0 and 2 pi. Okay. So we'll use this substitution. So what kind of relation we have for in this case would be, let's see what we get here. Here, this is r squared cosine squared. Here you get r squared sine squared. So you take this r squared out, cosine squared plus sine squared. This is 1. Okay. So you get these relations. Okay. So then it justifies us to compute this one. Is used to reduce number of variables. Okay, so for example, this one here, sine x squared plus y squared over. Okay, let's see. And by substitution using this one, we just say this is polar substitution. You get sine r squared over r squared. Okay, so here you have two variables. Here you only have one variables. Okay, and as one variables, you can use L'Hopital. Okay, so this is the case. Limit using polar substitutions. You get it's put directly here. It's sine r squared over r squared. Okay, because the angle is the same as this one, we know this is a special special trigonometric form. Or you can use L'Hopital. So you get only 1/3 because this limit is 1. Okay. And this one, so this is again polar substitutions. So you get in this case it would be see this is r cosine theta, r sine theta over here you have r squared. Okay, so this cancel the r. So at the end you have cosine theta sine theta. However, this value uh, pretty much depends on theta. So, all right, so different theta gives you different thing. So it's when this is limit doesn't exist. Okay. All right, so that's the question of the limit doesn't exist and polar coordinate. Questions? Okay, let's go back to say continuity. Same with the one variables. Function is called continuous if the limit is the same as the value. So the case when we plug in numbers to give you the limit, then that's exactly the case of continuity. Okay. All right, and composition of continuous functions is continuous. So we just use this one. Okay. All right, so let's do some more problems. Let me just mention a couple. Continuity. Uh, have just two variables. At the point AB, if the limit approaching the point AB also F. So then this is the continuous one. Okay, and we just use this as fact to compute this. All right, what's the example? Okay, so the question is, find all points xy for which the following function are continuous. Okay. So problem A, let's just how you add this system. The question is, find all pairs xy such that the function, this is how it's defined, 2x plus 3y over y minus 4x squared is continuous. Okay. All right, so we notice then this is rational function. As rational functions, this is defined if the denominator is non-zero. So in this case, y is not equal to, right? So then this is a, how you call this? It's parabola. Okay. So as long as you're not in the parabola, then you'll be safe. Okay. So first you put that the domain. Domain is all points, all pairs, such that y is not equal to 4x squared. So that's the domain. Okay. And as the rational functions, this is x plus 3. And this is polynomial. And this is continuous. This also continuous. And as rational functions, So it is continuous. Whenever denominator d is not equal to 0. Okay, so that's why the continuity means that the same as t. Okay, therefore is continuous in its debate. Okay. Right. All right. F cosine of this, right? Okay. The x cubed minus 4xy plus y squared, that's a continuous. And cosines is the compositions, continuous functions. Again, this is continuous. Okay. All right. Accept. Skip that one. It's just the terminologies. And for the mixed partials, we discussed this yesterday when we discussed the mixed partials. The derivative are the same. Okay. So uh, again, let's do one more problem. Uh, one more problem for this one. Uh, let's do this one here. Okay. F is continuous in the whole plane. Find formula for G. All right, so let's do this one here. Say, according to this one, um, okay, so let's do this is not defined at x minus uh, at x equals to y. Okay, but then it must be here. Okay. Um, so the question is, what is g here? So that's f is continuous. So the limit is okay. So how to find g? To find g. Yeah, next. Okay, so that's the g here should be the limit of the function of function. This kind of limit. Uh, So when AB is on the line equals to Y. So in this case would be this is A, X is to Y. Sorry, this should be should be this limit. All right, but let's check this one here. Somehow we can reduce this one. You can simplify this one. You can factorizations because we can factor this out. This is right here because you can factor this way, and here, so you can cancel this one. So you end up with. So as long as you're not on this line, then you can compute this. Is actually this one. Okay. Actually this one. And on the line that x equals 2b to y. Okay. Then this gives you actually 2y. Okay. Right. It's 1/2. Okay, this is our AB. Okay. So this limit. This is our, let's see, F. Okay. Okay. So this is actually simplify the limit just in terms of x. X equals to let's see, a on this line comes this. This is after factorizations. Okay. Then this becomes x plus this 2y is just x. 2x. Okay, so it's 2a. Okay, so then what's the value of the g of x? Back to this question. What should be g? Okay, so then if you g of x is just 2x. Okay. Questions? So now the claim is that what's this? X squared minus minus. This one is This is continuous. Uh, all right. Okay, so that's the end of the section of limit and continuity. Questions? All right, so let's do one more example. This one. So, okay, let's see. Give an f like this, and then we show that f of x approaching 0 as xy equals to 0 along straight line y equal mx. Okay, so that means limit of is to 0, 0, but y equals m of x. Okay, so then this reduces to just one variable, so x squared times m of x, mx. This is x to 4 plus, okay, let's simplify this, mx cubed. Here you have, oh, x squared, let's see, factor x squared out, x squared plus, yeah, okay. So you see, this cancel, this is just x, okay, because this x, this limit is just 0, okay, equals to this limit. Just write this down. Mx over, okay, so this goes to 0, but this goes to m squared. So then this is it. Okay. All right, what does it mean is just when you approaching 0 with any straight approach, this is just always gives you 0. Okay, but then that is not enough because, let's see here, along the parabola, this is, so let's compute this along the parabola. squared. Yeah. All right. So then this limit. But y equals x squared. Let's rewrite this x squared y. For so then this becomes just one variable. Okay, so we replace a y by x squared, and you have x4 remaining, but then y squared is x. So you get x4, x4. So then these are not the same. Okay, so we found approaches that give you a different values. Any straight approach gives you 0, where any approach through the parabola gives you 1/2. Okay, so we have found approaches which give different value of limit. Scope of limit. It's not really limit. To say limit, it must exist first. Then limit does not exist. All right. So that's the. Any questions? All right. If not, then I'll stop here. And again, you will have a quiz on Thursday. So the second half of the tutorial sessions. All right, will be on the previous factors, parametric equations, factor valued functions. All right. Stop the share. Stop recording.